I'd like to make a few more comments about LMS algorithm. If you look at it, the next weight vector equals the present weight vector plus 2 mu epsilon x. What that tells you is that when epsilon, the error, is positive, you take the input pattern, multiply by 2 mu. Remember that mu is a positive constant. So 2 mu, you multiply that by x. So you're going to add this to the present weight vector to get the next weight vector. So the change is this. When the error is positive, you add the pattern, you add the x vector to the w vector to get the next w vector. When the error is negative, you subtract the x vector from the present weight vector to get the next weight vector. But the objective of all this is to make the error small. And the error is the difference between the desired response, in other words, what you want and what you've got. The error is the difference between what you have and what you want. So the error is going to be sometimes positive, sometimes negative. When it's positive, you add the x vector to the w vector to get the next w vector. When the error is negative, you subtract the x vector from the w vector to get the next w vector. Now I'll demonstrate that with a simple machine, an implementation of the Adaline neuron. Let's take a look. So what you have is a single adaptive neuron that will be trained with the so-called LMS, least mean square algorithm. The algorithm is known today as Woodrow-Hoff algorithm. In the field of neural networks, sometimes it's called the delta rule. But anyhow, it's the algorithm that was developed by Ted Hoff and myself. Ted was my first doctoral student. And we built this machine. The circuits inside were designed by Ted. We built this in 1960 is the date. The algorithm was developed late in 1959. Now the inputs are applied by, input patterns are applied by means of switches. So I'll show you what a T pattern looks like. So I think you can see that T pattern in the lights. Now switch up means +1 input, switch down means -1 input. So the inputs are +1, -1, not ones and zero like the usual binary. Each switch connects to one of these coefficients. And these are able to be rotated. And now what I'll do is it looks like I'm turning them all off. Actually, all those that are off, you should realize have -1 inputs. But the weights are set, I set them initially to 0. So they're all 0. So here is an input that goes to this weight, this coefficient. Or if you're a neuron guy, you call that a synapse. So this is an input to a synapse. Now, if I put the switch up as +1 input, and I make this positive, you can see the output has become positive. Now, if I put this down with a -1 input, the output goes negative. So positive, negative. Now, if I take this and put it back to 0, I can switch this positive and negative and nothing happens, because I'm multiplying this input by 0. Now if I make this negative, when I put the switch up, the meter goes down. When I push that down, the meter goes up. Now if I take these things and scramble them all up, do all sorts of funny things. If I apply an input pattern of some sort, then I'm taking this input pattern, +1s and -1s, and multiplying them by these coefficients, or these weights, or synapses, and you see the weighted sum. So the meter is showing the sum of this multiplied by that, plus this multiplied by that, plus this multiplied by that, this multiplied by that, and so forth. Now there's an extra one here. This is called the bias weight. The input to that is always +1. So if I take this positive, it makes the response go more positive. If I make it negative, it makes the response more negative. Doesn't matter what the response is, it adds an additional bias. Okay, so that gives some idea of the structure of this thing. So it's sort of modeling, in some sense, a human neuron. So we bring this back to 0. I can start out with 0 as an initial condition, because I don't know whether these weights are going to go negative or positive, so I start out with everybody 0. Don't have to do that, but it's just as easy. So it doesn't matter what I've got here, the response is 0. So now what I will do is to train this thing. I'll put in an input pattern, a T pattern, and I'll train it to give a positive response to the T pattern. Then I'll put in a J pattern and train it to give a negative response to the J pattern. So let's put back the T pattern. There's a T. Now, I want the response to the T to be positive. So the error is the difference between the desired response, which is positive, let's say +1, sort of out here on the scale, and 0. So the difference between positive and 0 is a positive quantity. So therefore, to get this thing to go positive, what I want to do is to take the input pattern and add that to the weight vector, add the pattern vector to the weight vector to cause the response to be more positive, to get closer to the desired response. So now, this input is +1. So let's say I go 1, 2, 3. 3 clicks. This is positive. This is positive. This is negative. This has got a positive input. This is a negative input. So I go negative. This is negative. This is positive. This is negative. This is negative. This is positive. This is negative. This is negative. This is negative. This is negative. This is positive. This is negative. And now you see we got a good strong positive response to the T pattern. Now let me put in the J pattern. Yep, that's a good J pattern. For that J pattern, let's say I'd like the response to that to be -1. Okay. Now, the desired response is negative. The actual response is approximately 0. So the difference between the two is a negative quantity. So that says to get what I want now, I need to subtract that pattern from the weight vector. So this is a negative input. To subtract negative, I go positive. This is negative, so I go positive. This is positive, so I go negative. This is negative, so I go positive. This is a positive input, so I go negative. Notice that every time I do this, the response is getting closer and closer to the desired response. This is a negative input, so I go positive. Positive input, I go negative. See, did I do that right? This is a negative input, so I'll go positive. Negative input, I'll go positive. Positive input, go negative. Negative input, go positive. let's see, this is a positive input, so I'll go negative. This is a negative input, so I go positive. Negative input, go positive. Positive input, go negative. Positive input, go negative. Positive input, go negative. So you see we've got strong negative response. Now let's put back the T pattern. So the T is giving a positive response. The J is giving a negative response. So we trained it on two patterns. Now suppose that I'd like to shift the T over by 1 pixel, translated, and train it to give a positive response. Now I'm having a problem because the T, this T, has a lot in common with the J, the untranslated J. And since the J was trained to give a negative response, when I look at this T, it's giving me a negative response, but I want it to be a positive response, so the error is bigger. I want the response to be way over here. The error is bigger, so instead of using 3 clicks, let me do 4. So this is a negative input. I want the error is now a positive quantity, so I want to add this pattern to the weight vector. So this is minus, so I go negative. This is positive input, so I go positive. This is positive input, so I go positive. This is positive input, so I go positive. This is positive input, go positive. This is negative input, go negative. Positive input, go positive. Negative input, go negative. Negative input, go negative. Negative, go negative. Negative, go negative. Positive, go positive. Negative input, go negative. Negative input. Positive input. Negative input. Negative input. Okay, so now I'm getting a positive response. Let's try the 2 patterns that we put in. The original T is there, that's good. And the original J was there. It's giving a negative response, so it's giving the right answer. It's a negative response, but it's not strong, it's been hurt because of the conflict between that J and this shifted T. So let's go on. We'll put in a shifted J and train it, translated J, train it to give a negative response. So we're going to subtract that pattern from the weights. So this is minus, means we go plus. And this is minus, we go plus. Can't go anymore. This is minus, go plus. This is plus, go minus. Plus, we go minus. Plus, we go minus. Minus, we go plus. Minus, we go plus. Minus, we go plus. Minus, we go plus. Plus, we go minus. Minus, we go plus. Plus, we go minus. Plus, we go minus. Plus, we go minus. Can't go anymore. Okay, so now we've got a nice negative response to the J. Let's go back and check all of our patterns. So here is a T, and there is a J. So it's been hurt. We can fix it. Here's a T. There's a J. Well, let's make the original J, the response to that, stronger. So we want the responses here. The desired response is further down. So now the error is a negative quantity. So we want to subtract that from the weights. That's minus. Subtracting it means go plus. I give it 2 clicks. So we don't have that far to go. This one can't go anymore. This one is positive, so we go negative. This one is negative, so we go positive. This one is positive, so we go negative. This one is negative, so we go positive. This is positive, we go negative. Negative, we go, where am I? Negative, negative, we go positive. Positive. Negative. Positive. Negative. Positive. Positive. Negative. 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 Can't go anymore. So let's see what we got. Here's the original T. It's plus. That's good. The original J. It's negative. Nice. The translated T. It's a good response. Positive response. And the J is giving us nice negative response. So we've solved the problem of training it for T and J. And look at the weights. You can look at the pattern of the weights and you can't see very much. You can't figure out how the system is doing that. But what it did is just follow the LMS algorithm, and it's able to separate the T and the J and the shifted, translated T and the J. And that's how we train this Adaline. We call it knobby Adaline because it's got all these knobs. So this is manually trained by using your fingers. And then pretty soon we'll take a look at an automatic one where you don't have to train it all with your fingers. So anyhow, you notice that when you train in a new pattern, you tend to disturb the patterns that are already in there. So you have to go through all your patterns and train them over and over again. So the training process is not like recording where you record it once, but it's an iterative process where you have to go over and over and over again, lots and lots of cycles through all the training data until you're getting the response you want for all these input patterns. So it's an iterative process. And it can be proven that this is a process that converges. And this is a process that this basic algorithm is used in every modem in the world. The technology involved in this training algorithm from 1959 is one of the fundamental technologies of the internet. Without this algorithm, you wouldn't have an internet. So it's one of the technologies. Many technologies had to come together to do the internet. Anyhow, I'll show you next how to train an Adaline that has electronic synapses. What I'd like to demonstrate next is an Adaline that does the same as knobby Adaline, except this one is called a memistor Adaline. A memistor is an electrochemical cell that works by electroplating. So the cells are little tiny, they're like the size of a flashlight bulb, little tiny cell. And there's a resistor inside, and there's a source of copper, and the cell is filled with a fluid of copper sulfate and sulfuric acid. This is a copper plating solution, and you plate copper from the electrode, which we call the source, and you plate that down onto the resistor element, which we call the substrate. So you plate copper from the source onto the substrate, and what this does is it makes the electrical resistance of the substrate go down, and when you reverse the plating current, go the other way, you can make the resistance go up because you remove copper from the resistor element and put it back on the source. So by electroplating, you can make these resistor elements take on any value that you like, and you can make coefficients from these elements that would be positive or negative, depending on how much plating is on the substrate. Now this let me put on an input pattern. That's a T pattern. I think with the bright lights you can see that that's a T pattern. So remember that the switch up is a positive input, the switch down is a negative input. And you can get an idea of the value of that particular coefficient, because when I switch it, some of them go like that, some of them go the other way. So when I push it down, that goes down. I push this up, it goes up. This one, when I push it down, it goes up. So this weight is a positive weight. This one is attached to a weight that happens to be negative. Now what I did is earlier, before recording this, I trained this thing. So I've already trained it, and I'll show you what I trained it on. So there's a T pattern, and I trained it to give a positive response on the T, and I trained it to give a negative response to the J. I also trained it to give a positive response for the translated T, and to give a negative response for the translated J. I also trained it to give a positive response to a T that's rotated by 90 degrees. So the T is giving a positive response. I trained it to give a negative response to the J. Then I trained it with a T pushed down by 1 pixel. That should give a positive response. And the J pushed down by 1 pixel to give a negative response. So we've got a vertical TJ, then shifted TJ, then a horizontal TJ, and then shifted down TJ. So in all those positions, the T is giving a positive response, the J is giving a negative response. So I wanted to show you that. What I can do is I can put all the switches up. Put them all up. And by this is the adapt control. So when I push this to the left, what I'm doing is I'm taking what's here, what this pattern is, I'm subtracting that from the weights. What that's doing is it's deflating every one of those electrochemical synapses. We're making them more negative because all the inputs are positive. If I push this to the left, then what I'm doing is removing copper from all those substrates. Everything that it learned, I'm wiping it out. So we have to learn again, show you how that learning works. So now if I push this again this way, I can bring it back on scale. You see it has an analog memory. So I give it the slightest little touch. Just give it a little touch. And what I'm doing is I'm plating a few molecules on each of these little cells. The copper is plated down 1 molecule at a time. So it's smooth and continuous. Because every time I do that, you've got God knows how many molecules you're actually moving around. Lots. So with all inputs plus, when I push this to the right, I'm adding copper to all those substrates, making all the synapses more positive. When I push this to the left, I'm making all the synapses less positive. So if I go like that, I can strip all the copper off. So whatever it was learned, I'm erasing it. So now I bring this back on, and let's see, we'll put the T in, and we want a +1 response. We want a positive response to the T. So we do that. Now, for the J, we want a negative response. So what it's going to do is to subtract this pattern from the weights. The J is already negative. So, half the time you're going to be lucky. Now let's put the shifted T, the translated T. That's positive. We're lucky again. We're super lucky. The J is negative. So the T is positive. J is negative. T is positive. J is negative. Now let's try this guy, the horizontal T. Well, it's just slightly positive. Let's give it a little jolt. Make it more positive so it's a little more solid response. There's a J. We want to make that negative. T is positive. J is negative. Now let's lower the T by 1 pixel. We want that to be positive, so we're going to make it positive. There's the J. We want to make that negative, and it already is. So let's try this T. Horizontal T is positive. That seems happy. J is negative. T is positive. J is negative. So all the horizontals are now in. But by putting that in, we've probably done some damage to the verticals. Okay, now let's check the verticals to see what damage we did. The T has some damage. It's now reading negative. It should be positive. There it is, positive. J is negative. That's good. This T is supposed to be positive, but it's having a fight with the J. That J is negative. That's good. Let's check the verticals again. There's the T. That's supposed to be positive. Give it a little juice. There's the J. It's supposed to be negative. Well, we're having a fight between this J and this T. That T is pretty solid. And here's a J. So the verticals are all in now perfectly. Let's see what damage we did to the horizontals. T is positive. J is supposed to be negative. Uh-oh. Let's lower the T by 1 pixel. It's supposed to be positive. J is supposed to be negative. So the J is good. This T is good. The upper T is good. The J is good. So the horizontals are now solid. Let's check the verticals. Whoops. T should be positive. J is negative. That's fine. T, well, give it something. J is just fine. Let's check this again. T is good. J, give it a little more. T is good. J is good. So the verticals are fine. And let's check the horizontals. T is there. It's okay, but it's not strong. J is bad. Let's fix that. Try this T. That's fine. J is fine. So let's check them again. That's good. J is good. That's good. Let's check that one. That's good. That's good. So now the horizontals are solid. Let's see what the verticals look like. That's a T. That's fine. J is fine. T is fine. J is fine. I think we got them. How do you like that? They're all in there. So we should take a look to see what these memistors look like. They're little electrochemical cells. All the electronics here is from 1963. You can zoom in a little, and June. You can see the memistors are here. There are 17 of them. So there's 16 inputs on the input pattern, plus the bias weight. Each of these cells is in a little metal can, and the cell is the electrochemical cell is inside that. And so there they are, and all this is part of the electronics. All these circuits were designed by Ted Hoff way back in the early 60s. And this is, I have to tell you that not all of these memistors are still working perfectly. Some of them, a few of them, are not adapting, are not training at all. However, this least squares method, what it does is it causes the memistors that are operating and intact to take over automatically the function of those pieces that are defective. So this is a device that can work even in spite of the fact that some of the components are not working properly, because it's adaptive. And the thing is that if you were using this system and pieces of it were dying out on occasion, the only way to get it to do things that you want it to do is to keep on training it. So I think possibly in the human brain, your neural nets, pieces of them are dying out. The only way to make the neural nets in the brain work is that they have to be constantly trained. And they will work in spite of defective parts. And I think that possibly what happens while you're asleep is that you're training these things. But this is a whole nother story, so we can't do all that right now. Anyhow, this is Adaline. This is memistor Adaline. And you've already met knobby Adaline. They both do the same, but this does it. The synapses are electrochemical. So I think you can see where the inspiration came from for this system. Hoff and I patented this thing back in 1963. That was my first patent. And we had patented the LMS algorithm, the training algorithm, and the electrochemical device, the memistor. So this is quite an old device. It's an analog memory device. It's pretty hard to do analog memory with electronic components. Anyhow, thank you very much for watching. Goodbye and good luck.